Hello everyone and welcome back to my YouTube channel. I am Krishna Pandey and welcome to the 10th video in our machine learning series. Today we will explore the fascinating world of dimension reduction. We will cover its definition, importance, technique and practical implementation like identifying multicollinearity and performing principal component analysis PCA using R and Python. By the end of this series, you will understand how to simplify data using retain while retaining valuable insights. Let's begin. Dimension reduction involves reducing the number of input variables in a dataset while preserving as much essential information as possible. Why it is important? It simplifies complex models, making them easier to interpret, reduces overfitting by eliminating redundant or irrelevant variables, improves computational efficiency, saving time and resources, enables better data visualization, especially for high-dimensional datasets. There are two main approaches to dimension reduction. Feature selection. This identifies and retains the most important variables in the dataset. For example, techniques like recursive feature elimination, that's RFE, feature extraction. This transforms the data into a lower dimensional space. Principal component analysis (PCA) is a popular method here. Multi-collinearity occurs when independent variables in a regression model are highly correlated. Why is this a problem? It makes it difficult to determine the unique effect of each variable, increases the variance of coefficient estimates, leading to a less reliable prediction. To detect multi-collinearity, look for high pairwise correlations. Check if two or more variables are strongly correlated. Variance inflation factors (VIF). If VIF exceeds 5 over 10, it indicates potential multicollinearity. Here's how to identify multicollinearity in R. Load the dataset and fit a regression model. Use the VIF function from the car package to calculate VIF values. Interpret the result variable with a VIF greater than 5 may indicate multicollinearity. This helps pinpoint problematic variables, allowing us to address them effectively. In Python, we follow a similar approach. Import necessary libraries and load the dataset. Add a constant term to the data for VIF calculation. Use the variance inflation factors functions from states models to compute VIF for each variable. Review the VIF values and address variables with high multicollinearity. PCA is a dimensionality reduction technique that transforms correlated variables into a set of correlated components called principal components. Its key concepts include each principal component is a linear combination of the original variables. Components are ranked by the amount of variance they explain. The first few components capture the majority of the variance in the data. Here's a step-by-step guide to perform PCA. Standardize the data. Ensure variables with large scales don't dominate. compute the covariance matrix, understand relationship between variables, compute eigenvalues and eigenvectors. Eigenvalues represents variance and eigenvectors defines the opponent's directions. Transform the data. Project the original data onto the principal components for a lower dimensional representation. This process helps simplify the dataset while preserving the critical pattern. And that's a wrap for our session on dimension reduction. Today, we explored the importance of simplifying data, tackled multicollinearity, and learned how to perform PCA using R and Python. If you found this video helpful, don't forget to like, share, and subscribe to my channel. Feel free to drop your questions or feedback in the comment section. I did love to hear from you. Thank you for watching, and I will see you in the next video of this series. Wait for the next video.